thinking. Still thinking.
I didn't get the recording in progress thing.
Okay, I believe we are live. Um, yeah, welcome everybody. We are super fortunate to have Fritz here today to share their work on high performance eGraphs on multi-core CPUs. A thing that many people have been focusing on, sort of high performance things, and I'm really excited to see what Fritz's angle on this stuff is. So, Fritz, we can see your screen. Please take it away when you are ready.
Great, thanks, and thanks for organizing the seminar and the Zulip and the whole community. It's great, mostly to lurk, I guess, but um, it's great to read all your papers. So today I'd like to just uh, have a discussion about engineering details around engines for eGraphs and logic programming. So I've used egg at work, but today I'll be talking about a much less general system for a particular algebra. I built a system back in grad school, and I've been maintaining it on and off as I worked in as an engineer and some performance engineering roles over the years. Okay, so let me just start out with the limitations of this system versus egglog, to frame to frame exactly what it does. So the language I'm interested in is quite narrow. Um, it's untyped. I think that's the biggest restriction. I'm coming at this more from group theory, like, let's see if we can generalize Todd-Coxeter and handle, non-associative algebras. I'm not coming at it from like computer science or logic programming, but really from an algebra perspective. So my theory is pretty narrow. I'm interested in just a small family of theories, but it's complex enough to warrant a rule compiler for semi-naive inference, and the rule compiler the rules can trigger new e-nodes, new relational facts, e-class mergers. So it's not just pure data log, but no new e-classes. So I've tried to trigger e-class creation in the past, and everything's just blown up. I haven't I've never mastered the skill of preventing blow up. Maybe I could learn something from you guys. Um, I also have yeah, I've just hand coded the e-class creation. Mostly I just enumerate like the simplest few terms or insert terms of interest and then work with all the e-nodes that are created around those. But given these restrictions, I'm pretty happy with the performance results working on this, for since 2005. I can build these big kind of dense e-graphs with tens of thousands of e-classes, but billions of e-nodes and billions of relation facts. Um, I use a lot of memory to do that. I use a lot of cores. Read that 96 cores with a grain of salt. I think it scales pretty well to 32 cores. I just used a 96 core machine to get this plot because I ran out of memory on my EC2 instance and didn't have time to turn up the memory, but with just 32 cores. But it does scale pretty well to 32 cores. Okay, so those are the restrictions. Here's
Fritz,
how
can I jump in? Like
yeah.
the no new E classes thing, what does that really mean? I kind of didn't follow that statement.
Okay, so I have an eGraph represent so some software that has an eGraph representation and an equality saturation engine. And the representation has the interface that you can manually insert new e-nodes and e-classes into that using various heuristics, scripts that say like, oh, enumerate the simplest million terms and insert them in the eGraph, or enumerate the take a particular AST and insert it in the eGraph. But then when I trigger equality saturation, none of my rules trigger creation of new e-classes. They're only kind of data log plus merge triggering.
So this is a property of your rules more than of your engine.
Uh,
Or is the engine specialized to this in some way?
that uh, let's see. I guess I think so. I guess I think of the equality saturation engine of it doesn't have a way to allocate new E-class IDs within the rule execution. Like there's a virtual machine. It has ops. There's no op that says create a new E-class. It can merge E-classes, but the the kind of logic programming engine it's only like halfway between a logic programming engine and like the egglog, in that it can merge, but it can't create new E-classes.
Got it.
So I have all sorts of different extra, heuristics that are outside of the engine to create new E-classes, enumeration, and then inserting terms, and then statistical things. But I haven't found it useful to. Again, I've never mastered the skill of writing rules that don't blow up. So that's why, uh, yeah. Um, okay, so I'll start by talking about the language I'm interested in, and then ask you to have patience as I just described the data layout. So most of the work in the engine is about making sure it's cache friendly and having locality, temporal and spatial locality. And then I'll go through, given the data layout, I'll go through some particular rules, compiling sequent rules down to semi-naive like query execution plans. And then uh, that'll build up an idea of single-threaded operation. And then I'll talk about parallel execution. And then finally, I'll talk about kind of the sort of eCraf analyses I do in this system. Okay, so the language I'm interested in is like pure untyped lambda calculus or pure untyped combinators. They're, modulo beta, they're equivalent beta eta, they're equivalent, and they have a super simple grammar. This is like a programming language over 100 years old. The simple grammar has three nullary functions. The simplest version of this grammar has three nullary functions and a binary function. And just the simplest version has three rules, right? There's an identity function, a constant function, and this kind of cute substitution function. And the cool thing about combinators is that they have this sort of poor man's lambda binding, where you can represent higher order functions, but using kind of a first order language using this abstraction. So you can read this abstraction as kind of a poor man's lambda x dot. So the identity allows you to convert variables to functions. The constant allows you to ignore variables that don't occur in an expression. And the S combinator is this kind of substitution function that allows you to abstract to recurse down into the subbodies of an application. And this is actually this bracket abstraction in combinators is actually really nice for eGraphs. Roger Hinley in the 60s published this really nice axiom schema that can generate. In the paper, he talks about a particular system, but you can really think of this adding on to any combinatory language. It's a way to generate finitely many ground equations, such that if you initialize an eGraph with those equations plus the beta rules, the result is obeys strong reduction, or that it's extensional, that it obeys like the combinatory version of eta conversion. And so I leverage this fact in my system. I thought you guys might be interested in this because it's kind of an alternative to slotted eGraphs and binding. It's like one way you might do binders and eGraphs. That's the only reason I mention this, but I use this quite a bit, and I have some nice, rules that generate these axioms. So in practice, the language I deal with, it's a little more complex than just the SKI combinators. I have 21 nullary functions this month, 5 binary functions. I'm also interested in adding. I'm a big fan of Dana Scott. He lives in Berkeley there. I'm a big fan of Dana Scott, and I love his lattice theories of lambda calculus. And so I work with a join, and that's like an extra combinator that obeys the ACI laws. And then Dana has this beautiful theory from the 1970s about treating kind of simulating types in an untyped system using closures, that is increasing idempotence with respect to the Scott order. So I do that too, and it's again it's kind of a way of getting some type theory without paying the cost of all the type theory plumbing, but the cost ends up being E nodes. So that's, with tens of thousands of E classes, you end up with billions of E nodes. So you pay for E nodes instead of plumbing. Instead of just the beta and eta rules, I'm interested in stronger theories as well. From the E-graph perspective, there's this theory called H star, which is the theory of, Scott's models of lambda calculus. So H star is a really cool theory for us E-graph people. It's Hilbert post-complete. So Hilbert post-completeness of an equational theory is the property that if you add any equation, the whole system collapses. So you can think of this Hilbert post-completeness as being maximally coarse. It's like you have the most E nodes per E class in your E graph. So this is the theory I'm interested in. The problem is it's not decidable, so I can only ever approach it right with finitely many axioms. It's pi02 complete, so it's actually doubly undecidable. But between Hindley's axiom schema and these H star equations I have to hand prove, I end up with like on system startup, there's thousands of ground equations to kind of pre-populate. There's a little bit of issue there. So I try to avoid creating new E classes again when possible. And so I do a couple tricks to insert all these ground equations without having it, create excessive E classes and then crash back down. So one is like I hash const the expressions and do some like kind of optimal insertion order so that early equations are leveraged before building up larger equations. And then I'll do like insert a few equations and then saturate and then insert a few more and saturate and do this kind of batch thing. So that allows me to create a smallish E graph without getting, excessive memory growth and then having to squash back down. And then again, I have these tens of rules. Instead of this, 100-year-old S rule that Moses Schoenfinkel came up with back in the 1920s, not the 2020s. I split that up instead of an S combinator, I use a binary function. So that costs extra memory, but it simplifies the matching patterns in the engine. And then finally, in addition to just function symbols, there's a really natural partial ordering on lambda terms. This is like Dana Scott's information approximation order. If a term diverges, so this is the order where if a term diverges, a non-terminating computation, you can think of that as the bottom element, and then you can refine that. And so I have axioms for this less, the partial ordering axioms and monotonicity with respect to all these functions for the partial ordering. And then the system I have also represents negation. So it represents it has two unary relations and one binary relation, and then for each of those, it also has the negation of those. Okay, so now I've described the relations and the functions, let me describe the layout of these things. So let me start with binary relations first because they're simpler. So I have this general compiler that in theory like works with any binary relation, but in practice, I've, in 20 years, I've only ever had these two, relations, less, and it's, I'll call it less. It's really less than or equal to, but less, and it's negation and less. So each of these I represent with a dense bitmap matrix, actually two matrices, one column oriented and one row oriented. And so the compiler will use whichever one has better locality for the particular place that it occurs. And that also allows me to do like SIMD bit set intersections and differences. And in practice, so I'll try to provide some actual numbers. Unlike egg, I'm an egg log. I'm focused on just one theory. And so I can give concrete numbers like the less table is 4% dense. And the n-less table is 96% dense, and the union is 90, it's over 99. I think it's closer to 99.8% dense. And so that helps me I have these really concrete numbers. I'm in this wonderful scenario compared to you guys where I don't have to deal with like customers on the other side of a corporate barrier. I know exactly the model, and so I can hard code the compiler to say like, oh, I know that this table is, this dense. So that allows a lot of performance optimization. Okay, so binary functions have a representation in a data representation a little more complex than the binary relation. So I start out with an absence presence like the definedness tables, and those are just like the binary relations. I have a pair of bit set matrices, one row oriented, one column oriented. Because this is an untyped language, in theory, the functions are total, that any function can be applied to any other and any argument. But of course, in the finite E-graph, only some of those are. So it's partial by implementation, not by theory. And then the dense tables. This is like probably the biggest engineering decision that the lookup tables are these dense cache line blocked lookup tables with 16-bit E-class IDs. It seems crazy to use a dense table for a huge E-graph, but it turns out that these things are quite dense in practice. On average, the tables are about 12.5% dense. The application table, that's the densest of them. I think it's about 20%. It might be a little more than that, 20% dense. I'm not using join a whole lot, and so it's only about 1% dense, but I didn't bother implementing like a sparse table. I do have a second implementation for sparse E-graphs that has almost the same data layout, but uses a hash table for this. And that engine ended up being about 10 times slower in equality saturation than this dense. So the data access patterns really do help. Like I end up needing a lot of memory, but it's really worth it.
I had a question, if it's okay to just
Yeah,
interrupt.
please.
So the dense lookup table, why do you need it? Why aren't the bitset matrices enough? Why can't you index into those directly? I think I'm just missing something here.
Oh, right. So these are binary functions. So these so the binary function says like given a left-hand side and a right-hand side, what is the value? So the bitset matrices are just 1 if there is a value and 0 if there's not.
Oh, they don't contain the values themselves.
They contain only, yeah. So they're 1/16 the size. But the nice thing is I can do big SIMD bitwise operations here and iterate only over the presence. I'll show you some queries on the next few slides.
Yeah, great. That answers my question.
Yeah,
Thanks.
thanks for the question.
So that's helpful for the bitset matrices. Can you say a little bit about what the type, I guess, for this cache block lookup table? What the key is an E-class ID and the value is
it's a uint 16, like a 16-bit integer. Actually, it's 2. So there's a left-hand side. They're all binary. That's another they're all binary functions. So the key is a left-hand side and a right-hand side. So it's a pair of 16-bit IDs.
Hmm. And the output is
also a 16-bit ID.
Okay, so the key space here is 32 bits.
That's right. Yeah.
Okay.
So yeah, that's why it's 8 gigabytes max. So it's 32-bit keys and then times 2 byte per value.
Okay. Wow. And this and that's dense or somewhat dense? Like that 32-bit key
Yes,
space like
it's
actually
more
gets filled
than
up?
on average, they're more than 10% dense.
Wow.
So
sorry.
okay,
Oh, go ahead.
so Datascott has this beautiful types as closures theory, and the way it works is that if you have a type, you can apply it to anything, and it'll kind of coerce using a monotone increasing idempotent function. It'll coerce it to the next highest thing, and so you can apply like any function to any other thing, and it'll kind of like round up in the space of fixed points of the type. So usually it rounds up to top, which is like the top element of the lattice, which is the error element. So it's basically, there are a lot of errors in there, and there are a lot of constant functions too. So it turns out so I have this grammar, a probabilistic context-free grammar. So I fit this to data Like I have, some programs expressed and then fit this grammar to the data, and it turns out that like the K combinator is actually pretty useful, and that means there are a lot of constant functions in there. So last time I checked, about half of that table was filled up with constant functions entries. Like, and sure, I could be smarter and reduce that by a factor of 2, and then maybe be sparse. But so again, let me say that a different way. This 12.5, percent density, that might only be like 6.25, like where half of it is like the constant functions that maybe you could be smarter about. But there's still half of that that's not constant functions. That's still a lot of functions.
Right. Sorry, I have one more question.
Yeah.
16-bit E-class IDs is a little spooky in some sense. But I guess this is playing into your constraint, I suppose, where you're not creating any, like, is 16 bits enough, right? That's not that many E-classes, right? 2 to 16 is just not that big.
So, so the, the, the thing is seeing number of classes, I'm creating all the E I can.
Hey Fritz, we lost you a bit
Hello?
there.
Okay, yeah, I think that's on Fritz's side.
Sorry, it kills us the Wi-Fi. Sorry, are you guys back?
Yes, I can
Am I
hear you now.
back? Sorry about that. I think the
It's all
microwave
good.
kills the Wi-Fi. Somebody was running the
Oh,
microwave here. Sorry about
it's a
that.
classic.
Okay.
So 16 bits.
Yeah, so the thing I'm doing is creating as many e-nodes as possible for a given number of e-classes. And that's a lot of e-nodes, and I just can't, like, I've only recently been able to build e-graphs that could even come close to exhausting that.
Okay.
I do have another e-graph implementation that uses 32-bit e-class IDs, and it doesn't create, it's more of like a congruence closure e-graph. But then again, the equality saturation is about 10 times more expensive. So
Okay.
yeah. Okay, so oops. Okay, so the other piece of data is these indices. So you can think of the lookup table as the canonical data table, and then there are these database indices built on top of that to make queries fast. So because I'm using just binary functions, I can use compressed sparse row matrices, and these work really well. They're like value major. So given a particular value, there's like um, a sorted set of vector of tuples that have the left-hand side, right-hand side, and that makes the value pinned queries super fast. They're just like a sequential scan. The one issue with that is that if I fix like a value and a left-hand side to iterate over the right-hand sides, you need a couple binary searches to find where in the range that is, and that ends up being expensive. And so recently in front of that, I put a hash table. So again, I'm working with this like one system, and in this one system, 99.5% of those like left-hand side and value or right-hand side value pairs end up with either 0 or 1 entries. And so I can slap a hash map in front of that so that if it's 0 entries, it can just check that with 1 cache miss. If it's 1 entry, it can check that with again 1 L3 cache miss. And then if it's multiple entries, which happens in 0.5% of the cases, it can fall through to the CS tar table. So that sped up the system by 5 to 10% at some memory cost. But again, I can do that because I could, measure for this particular system exactly what the statistics were. Okay, so now that I've described the data layout, let me run through some examples of what the compiler does and how it compiles these sequent rules down to semi-naive query plans. So let's start with an example of this less rule. This is one sequent. It's the less monotonicity rule, right? So first, the compiler compiles like a negated version of that. By the way, when I write this rule, I mean there's another compiler step that turns the appfx and ffy into antecedents. There's some fy. So there's some compiler stages I'm skipping here, but the end result is that you get these 6 semi-naive inference triggers, right? So let's look at one of those and how, like, what comes out of the compiler, and then I'll walk through how it's executed. So describing both like the compilation and the execution in one example. So here's one of the queries. The way that works is given here are the kind of pseudocode instructions here. So first there's the trigger, which is that this e node exists, and then there's an iterator over another e node existence and a binary relation fact. So this looks at the presence absence table, and it can do a SIMD bit filter to walk through those. Then it does a local assignment, and then a conditional, and then finally, if it makes it to this stage, it learns a new fact. And so you can read this as a backtracking plan. If this conditional fails, it backtracks up to the for loop, and then continues on to the next. And this is a whole language, of course, and it can backtrack, and some of these are longer. And then 2 notes I want to make here are that this the way that the lookup table is arranged, this ends up being like a sparse sequential read here. So it has some nice memory locality because those are blocked. I can get like 8 values, loaded in a single cache line. And so it ends up having it's like this whole inference is it's gated. The biggest bottleneck is L3 cache misses. Like that's the slowest thing in the system. And so the whole system is oriented around avoiding L3 cache misses. And again, yeah, so it's not spelled out in this code, but the endless lookup table here is oriented in the way that it's FX major, so it can march around along those. It can load a single cache line of FX, which is for this plan it's fixed, and then look up different FY values. So that's done in the compiler. Let's look at one other plan from this example. This one's kind of interesting. So this is given FX and FY. There's this join here. So this is a CSR, compressed sparse row join, like a merge join. So it has 2 cursors, each walking in one CSR table, and they walk in tandem. And I only learned about how to do this trick last year, and for I think a decade I was missing this pattern, and this unless rule was the majority of the time taken by my system. And looking at it and staring at it and asking the AIs, and I eventually realized, like, oh, I'm missing a join pattern. And once I implemented this one pattern. So previously this was like 2 for loops instead of 2 cursors walking in tandem. And so once I implemented this merge join, then the entire binary relation inference of all of the binary relation rules went down to like 10 or 15% of inference time. So it went from the majority of inference time to the much less. So gosh, I wish I had known that earlier. Okay, I want to walk through 2 more example plans. These are the plans we looked at previously were just like logic programming. There were no mergers. So let me look at some plans that trigger mergers. And these are basic, this rule is from 1924. This is like basically Moses-Schoenfield's rule, except with, subs instead of app SX. So this is, we trigger here, we do another of those CSR joins. And then there's a theory-specific filter. So one of the things my compiler does is it knows about the K combinator and constant functions. So as I said, like half of the E nodes are constant functions. So what the theory does is look through all the list of the rules in my rule files, and for every rule, it tries to substitute for each variable. For like K for X, it tries to substitute like KA for some fresh variable A, and asks like, hey, does this left-hand side, but with a constant function there, appear anywhere? If so, that is a cheaper duplicate of this rule. And that means the rules overlap. And rules with K, like empirically, rules with K, like the constant rules, are much cheaper than rules without K. Because you can drop things. I'm sorry, I'm kind of hand waving here, but the idea is to look for rule overlaps and then use the cheaper of those. So in this theory, there's a particular way of looking for the rule overlaps, and the compiler knows about K and the const unary relation. And so it can do this early filter before it does this table lookup. And this early filter is pretty cheap. You can load one cache line for the X and one cache line for the Y, and look up, oh, is this X there, and that is that Y there. And so it ends up speeding up this. So that change to the compiler, it took a few days, but it led to a 30% speed up, like end-to-end system speed up, and it's like a nice isolated chunk of work. I needed to implement, some handling of the constant and the K stuff in the compiler, but it was a significant speed up anyway.
So did you it kind of sounds to me like you just added a separate rule that matches on the whether or not X is actually a constant applied to some fresh variable A, but or that's what it sounded like to me at first, but what you're describing here is you're sort of doing the first part of the join, and then you're doing some special parsing once you have matched, like these first two lines, we're applying for everything, and then we're doing special stuff for constants after that. Is that?
Yeah, let me try to explain it once more. So this rule here is one of a bunch of rules in my rule files. The compiler will look at every rule that it parses and see if there's a simpler version of that rule with constant substitutions. That means two rules overlap. If it does, then during the compilation of the more complex rule, it will insert these filters.
Okay, yeah. So in your rule file, you've already written the one with constants in it.
That's right. That's right.
Okay.
That's right.
Okay.
So it only does that. So the compiler can only do that if it knows that there are two other rules. So I wanted to minimize the fancy logic in the compiler and maximize isolate as much logic in the rule files as possible. Thanks for the clarification. Okay, this is the last plan I want to look at. And this one's kind of interesting. So again, we have some trigger. Again, there's this non-const filter that happens to be triggered. Here, there's a three-way bit set intersection. The compiler, in practice, it emits up to, I think, five-way bit set intersections. There's some pretty big bit set intersections there, and those are really cheap. You can use, count leading zeros operations and just march along those, and anyway, they're very cheap. And then at the very end, there's this kind of fused operation for the inference rule here. So usually the conclusion of a tactic is to create an E node or an E class in an E node, right? This one says that it's kind of a fused operation that says, like, does this E node exist and does this E node exist? If they both exist, it checks their E classes, right? If their E classes are the same, there's nothing to do. If they're different, it triggers a merge. If one e-node exists, then rather than creating a new e-class, it just inserts an e-node to the existing e-class and vice versa. So that's one of the other tricks I use to avoid at all costs creating new e-classes.
So if neither of those exist, does it just do nothing or?
That's right. That's right. Yeah.
Okay.
So if neither exists, it does nothing.
Oh,
yeah.
Okay. Interesting.
Yeah. Yeah. I guess again, it's like half a logic programming engine, and it goes like half towards egg, and then stops and says like, I don't know how to create new e classes because every time I've tried it blows up. And one question I have for you guys is whether worst case optimal joins would help. So in that one rule up, we looked at this rule with the original non-cons filtering rule, and there's this Cartesian product, or there's this join, like the CSR merge join. So what it does is it has like the two cursors and marches along with the z's, and then for every set of x's and y's, it enumerates over the Cartesian product of those y's. And I think, as I understand, these relationally matching worst case optimal join algorithms can restrict that Cartesian product. I don't know a nice way to code that up. So what I tried to do is at one point and gave up was to pull some of these filters up into the Cartesian product to avoid having to enumerate the whole thing. But the code seemed kind of complex, so I don't know. I don't know if there's an easy way to do that. Maybe somebody could ping me later.
Eli, do you have any thoughts on that one? Eli's the worst case optimal join person now.
Yeah, I think so. Yeah, I think that taking a step back, we should. I'm trying to make sure I understand. Is this even cyclic?
Yes, it is. It is
XZ,
cyclic.
YZ.
So there's
Oh,
an
yeah.
XZ, a YZ, and an XY down here.
Oh, okay,
Yeah.
that's what I was missing. Yeah, I think so in principle, right? Yeah, the worst case optimal joins should help here. I think the question is there a way to work it into your
Yeah.
indexing setup that doesn't, because if you like move from your indexes to hash tables, I'm sure everything would get like 10 times slower. So
Yeah.
so okay, but yeah, we should talk offline.
Okay, yeah, let's do that. Okay,
And,
so
the only thing that I'll add is like I think there is hope probably, because you have such a limited set of like everything's binary or whatever. Like I think it is possible that you in fact have all the indices that you need already, and it's just a matter of sort of implementing the interface of like instead of check, allow me to enumerate the things that, or walk, as you said, walk the possibilities of filling in a sort of partially constrained atom. So I don't know. It could definitely work.
yeah, that makes sense.
Yeah, you'd have
That
to
makes
flesh
sense.
out the details though.
Okay, so now that we've covered the data layout and how single thread execution, tries to avoid all three cast misses and maintain, march through the data optimally. Let me talk about how multiple workers coordinate. And so it's basically 4 steps. There's a bulk synchronous parallel, kind of four steps that just repeat in a loop, with barriers between every step, except for the execute plans and gather. There's not a barrier between those, but others are. There's a barrier. So let me walk through the steps one by one. So the first step is to build or rebuild those secondary indices, the compressed sparse row, those hash tables, and and this is parallelized with sharded tables. So I do like one table at a time, but then parallelize over the tables, data parallelism. The one issue here is that there are kind of 2 ways to build a table. The naive way is to rebuild it from scratch. the cleverer way is to look at the recent facts that have been learned and to incrementally update the table. And when that's possible, it's much cheaper. I'll show you some Perfetto slots if we have time. It's much cheaper if possible, but I haven't implemented if there was a recent merger, I don't know how to incrementally update, or I haven't implemented like the complex incremental update logic. So then I fall back to the expensive rebuild class. So that's another reason I try to avoid E-class mergers as much as creating new E-classes, and then try to avoid mergers as much as possible because the incremental build is much cheaper. And then there's this execution stage that's where the bulk of the work happens. So I have like a queue of antecedents, recent facts that were learned, and then a queue of consequence, these thread local, I think you guys call them mutation buffers, where the new facts are spit out. And that the execution consumes the secondary and primary tables. And this is completely embarrassingly parallel. These all pull from a single task queue, and there are millions or hundreds of millions. There are many tasks anyway. A couple notes here I want to make is that early on, these mutation buffers, these thread local consequent queues, were taking up a lot of memory. And so because there are many ways to prove a fact, there can be 1,000 different ways to prove any one fact. So one way to deal with that would be to hash them. But again, I am very averse to random writes. I try to avoid hash tables whenever possible. So instead, I wanted to use this log, like a sequential log of new facts that were learned. The sequential log was getting really big and using up a lot of memory. And so the design I chose was, because I'm using these flat tables for both the relations and the functions, I could choose one of those tables, like maybe the column-oriented relation table and the lookup table, as a canonical source of truth, and do an atomic write the first time I want to prove a fact. So for the table, for the relations, it's like an atomic OR, a fetch OR, and for the lookup table, it's a compare exchange, so it's a little more expensive. And then on that compare exchange, if the value was not there, the new fact is added. If the value was already there, the fact is discarded because it's already known. And if the value conflicts, then it instead switches to writing a merge. But that means, and so it's kind of a weird hack, and it only works because I'm using dense tables and because of monotonicity, right? We know that facts can only be learned. And so worst case, in the worst case, you might read, a user of that table might read a fact one stage before it should be published, but that's okay because of monotonicity and fixed points. And so that allowed me to massively reduce memory of those queues. I did that first for the binary relations, and then months later did it for the binary functions, and both times it reduced the memory by quite a bit. So now that's how I do these deduplication. The
Does
other
that
note
mean
I want to
that
make is,
writes take effect while the rules are running?
yeah, and it's okay because of monotonicity. Again, yeah, it was like one of those
You
things
can't
where
get
like
like a
most of the
cyclic
engineering
growth
work
this
is
way.
sitting for 3 days and convincing yourself that it's safe.
We've run into issues where you can have proofs that like use their own results as a premise,
Oh, wow.
without having like a barrier between those two. But yeah, I believe it's fine.
Yeah, I believe in this case it's fine. The other thing I wanted to mention is that early on, I had a lot of issue with heavy-tailed task skew. So I'd see some tasks that would take less than a microsecond, and then some tasks that would take tens of seconds. So like massive amount of skew.
What's a
And
task?
that's like a single antecedent that gets pulled off this queue and um,
Is that
executes executes
one antecedent through one like compiled rule, or just one antecedent?
it's one antecedent through one compiled rule. But actually, the compiler has a fusion stage, so actually those like programs
Sure.
they end up being trees, and so the biggest of those is like thousands of like it's a big program.
Yeah. Okay.
But some of them had really bad complexity, and those problems seem to just dissolve by implementing better iterators and these joins. So now I no longer see task skew. But anyway, that was a real blocker to parallelizing early on, and just kind of went away. Let's see. So after the plans execute, as soon as each worker finishes its last task, that is the antecedents are exhausted, then it merges all of its new facts into a global queue. And so these things, so first it sorts its facts, and the global queue of new facts is sorted, so it can do a log structured merge. And that's again, it's super fast. It's a two read heads and a write head zipping through memory, being friends with the hardware prefetcher, and it's super fast. In theory, I could do like log structured merge trees and merge these things in a tree, but it's so fast that I haven't even needed trees. And there's like a single global mutex, and every worker, when it's done, it just grabs the mutex and merges its stuff in. And I can show you later, but it's hasn't been an issue. It's super fast. And then finally, these facts are flushed, and that those atomic writes we did, which was a little sketchy, those are reconciled, and everything is kind of cleaned up, and that's also pretty cheap. Oh, okay. So I think we have a little more time. I just wanted to show you what these 4 stages look like in practice. Remember, rebuild, execute, gather, and flush. So I use Perfetto quite a bit. I'm going to zoom in, but this is Perfetto is a performance tool. I use Perfetto a lot and Google Perf Tools and pprof a lot for performance analysis. So this is on a 32 core machine. Each row here is a core, and time is on the x-axis. So let me see if I can zoom in. Okay, so I zoomed in a little bit here. So I could zoom in more if you want. Let me see. So the first thing to notice here is that this brown work and the yellow work, those are executing query plans, these tasks, and that's the bulk of the work. And again, the binary relation work is like 10 or 15%. It used to be the bulk of the work, and now it's no longer much. The next thing to notice is that this is the table building work here. So it's non-trivial, and when the system starts, it has to build the tables once. And you can see that there's a little tiny bit of inference work that happens here early on, and that triggers a merge, apparently. And so it has to rebuild the tables because I haven't implemented incremental table update. But then I'm pretty happy here. All of the subsequent table updates, because there are no mergers, we've avoided merging and just like inserted. It's like pure logic programming, just inserting these tuples, these enodes. Then it can do these really cheap incremental updates of those indices. And so here, the first one costs like so. Let me go back here. The building the indices from scratch costs over 3 seconds. The incremental update, the first one, costs like half a second. But then as the changes get smaller and smaller, you can see like as the work gets less and less, these incremental updates also get cheaper. So like here's one that's 73 milliseconds and 6 milliseconds, and they just get cheaper and cheaper. So even though it's like scanning through all that memory, there's not much to do, and it ends up being pretty cheap. By this point, it still dominates the execution work, but I'm pretty happy with the balance of index building and kind of the read heavy execution work here. Whoops. Let's see. Do I have enough time? Should I stop here and just discuss, or do you want me to talk about analyses at all, or?
I would be interested in hearing about analyses. Maybe we can just leave, 1 or 2 minutes to have some questions at the end, and we can always defer things to Zulip. But I'm interested in hearing about analyses.
Okay, sure. So I'm kind of coming at this from this weird perspective of group theory on the one hand and machine learning and classical natural language processing on the other hand. And the analyses in my system, I don't have any like frameworks, like fancy frameworks for analyses like you guys have in Egg and Egglog. They're all hand coded, but I do have a lot of like design patterns that I use for analyses, and I see analyses as an instance of semi-ring programs or fixed point semi-ring programs. I've done a lot of like probabilistic programming stuff, and we use semi-ring programs there. That's where you have like a sum operation and a product operation. So you sum over all the representatives of an E-class, or like the incoming E nodes. And then there's this product operation that tells you how to handle a particular E node, the different E classes that are connected to a particular E node. And it's a nice paradigm, and I think it's a little more general than just these semi-lattices or semi-groups. So one of the nice things is that semi-ring programming comes with like forward backward operations. So I mentioned earlier I can fit basis weights like these null and binary function weights to data like programs of interest. And the way you can do that is like by classic inside-outside algorithms from grammar fitting, NLP, natural language programming circa 2000. But you can do that modulo theory. It's like natural, old school natural language processing modulo theory with an eGraph. And so it's actually equivalent to like a um, automatic differentiation. Anyway, so I do a lot of these analyses, and I just wanted to show the design pattern that works pretty well that for me. All of my analyses use this kind of design pattern, or almost all of them, which is a gather-oriented hog-wild fixed point, I'll call it. So it's a fixed point because it operates until change, and I'm using mostly floating point analyses. And so I have like a threshold that says like, oh, operate until, 10 to the negative 2 tolerance or something like that. And then it's gather oriented in that I want random reads and sequential writes. So each worker can own like a cache line that it's writing to. And then it's hog wild in that I don't synchronize the reads and writes. So I use relaxed atomics here. And this is really nice. So in the spectrum of fixed point, or of these iterative fixed point algorithms, you can think of like on one end of the spectrum, there's a sequential version that does this read and then updates a value, and then all the subsequent computation has access to that value, right? And so if you have a linear graph, then you can do it in a single pass, and then it's like done, right? But if you have a tree, then maybe I guess if it's a DAG, you can do it in a single pass. But in eGraphs, they're not a DAG, so you still need multiple passes. And at the other end of the spectrum, you can think of like the double buffer parallel version, where you read from one buffer and you write out to the next buffer. So this hogwild, Ben-Recht style hogwild iteration is kind of a happy medium between those. So you have multiple workers and they're reading from a single buffer. And as soon as one worker is done, all the subsequent buffers or subsequent workers have access to that data. And in practice, it was like 10 times faster than the double buffer version in one, anecdotally. So it worked pretty well. I'll end there though. I'm running way out of time. Sorry.
Okay, yeah, well, I guess we are basically at time. Thanks so much, Fritz. This was super interesting. Is there somewhere like, I mean, feel free to post the slides on Zulip, and of course, this talk will be on YouTube. Is there somewhere aside from pinging you on Zulip where we can read more about, either the implementation or the setting to which you're applying this?
I have an old copy of this repo called PoMagma. It's at GitHub Fritzo PoMagma for partially ordered magma. But I haven't open sourced this. I don't have any publications. I would have published, but I thought like, oh, maybe I'll talk and see if anybody's interested first. So.
Well, I mean, I think even the link to the old thing would be great if we can put that in the Zulip. But yeah,
Oh, sure.
thanks so much. I'm sure that folks will be asking you some questions. I know I will on Zulip, so I'm looking forward to that conversation. And yeah, thanks so much, everyone, for joining.
Thanks for your attention, Ben.
Bye, everyone.